Hello everyone and welcome to the presentation of my PhD thesis. Today we'll be looking at the multi-physical simulation of ocean engineering systems with particular emphasis on the Modelica Ocean Engineering Library and a co-simulation methodology for drilling riser analysis. We will begin the presentation by looking at some background information regarding ocean engineering systems. I will then present the project objectives. We will then look at the development of component models for constituting the ocean engineering library. We will then look at the co-simulation methodology for drilling riser disconnect. I will present the methodology synthesis as well as results pertaining to the benchmarking of the simulations. We will then draw our conclusions based on the matter presented. Let's look at the sample case of a subsea installation procedure. The aim is to find the dynamics of the subsea suspended load. We can simulate this procedure if we have information pertaining to the environment, if we have information regarding the hydrodynamic particulars of the ship, if we have the relevant crane data regarding the subsea load, and data regarding the mooring line. One of the problems to be solved in the simulation is the hydrodynamic response of the platform. This is given by equations of the form that appears on the slide right now. We notice the presence of frequency dependent parameters like the added mass, potential damping, and the wave forces. These frequency dependent parameters are normally found out using a procedure called frequency domain hydrodynamic analysis. Let's look at the problem a bit more in detail. We look at the wave body interaction problem, where we consider a floating object interacting with incident waves. Three things happen. The incident wave changes the pressure distribution on the submerged surface of the body, and this causes the body to oscillate along its 6 degrees of freedom. A part of the incident wave is also reflected as scattered waves, and the motion of the object along its 6 degrees of freedom generate associated radiation waves that carry energy away from the system. Assuming linearity, the total effect of the wave body interaction can be split up into two subproblems. The diffraction problem, where we consider the effect of the incident wave and the effect of the scattered wave with the body assumed fixed at its mean position, and a radiation problem, where we consider the effect of the oscillation of the body along its 6 degrees of freedom and the associated radiated waves. The diffraction problem gives what is called as the wave excitation loads, which has two components. If we consider the loads exerted on the body due to the pressure field of the incident wave, then these are called as fruit coil of loads. And if we consider the loads exerted on the body due to the scattered waves, then these are called as diffraction loads. Considering the waves exerted on the body by the radiated waves, the component of that hydrodynamic load which is in phase with the acceleration of the body is called added mass, and the component that is in phase with the velocity of the body is called damping. From the force regime diagram, we see that depending on the relative size of the object in relation to the wavelength, we can specify different force regimes. And for a relatively smaller object, the diffraction effects are negligible. Again, considering that the object is small and so the wave making potential of the object is small, we can ignore the damping effects also. Thus, for a relatively small structure, the fluid loads can be expressed by the fruit coil of loads in case there is significant inertia and small drag, and the fluid loads can be approximated by using the Morrison formulation in case of significant drag and small inertia. In carrying out the frequency domain analysis, we normally use commercial software like VAMIT or ANSYS. First, we build the surface model of the platform. This is then imported into the hydrodynamic analysis software. It is split at the waterline and meshed. The wave directions and frequencies are specified and the hydrodynamic analysis is carried out. This gives the frequency dependent hydrodynamic parameters like added mass, damping, the full scale of loads, diffraction loads, the displacement response amplitude operators and the load response amplitude operators. Once we have this information, we can now attach the hydrodynamic parameters that we evaluated in the frequency domain hydrodynamic analysis to the vessel object and attach horizontal elements like the mooring lines, the winch wires and the suspended subsea loads and carry out the time domain analysis. This is normally done in software like Orcaflex. But what if your object of interest was the electrohydraulic crane itself and you wanted to simulate the dynamics of the load when, for example, one of the hydraulic hoses fail? The crane has influences from the mechanical, electrical, electronics, and hydraulic domains. And cranes are usually modeled using modeling languages like Modelica. So what is Modelica? Modelica is a modeling language for dynamic simulation. It uses the Acosel modeling philosophy. It is extensively used in the automotive and aerospace sectors. And it has a standard library with components and functions from many different domains. There is one open source distribution of Modelica, and that's called Open Modelica, and OIMedit is its graphics user interface. There are many commercial distributions like Demola, Simulation X, MapleSim, and Modelon. But in using the conventional software approach, we have a few limitations. Conventional ocean engineering software, like Orcaflex, does not have a multiphysics component library. And conventional multiphysics software, like Modelica, they do not have an ocean engineering library. So what do we do to overcome these limitations? For the first limitation, where there is a lack of multiphysics components in the ocean engineering software, the only solution is to develop co-simulation interfaces between the ocean engineering software and the multiphysics software, because most of the ocean engineering software are commercial and black box in nature and does not support the development of component models. For the second limitation, where there is a lack of an ocean engineering library in the multiphysics software, luckily Modelica is open source, the language itself, and therefore all the commercial implementations also support the development of component models by the users. The specific objectives of the project derive from the limitations and their solutions described earlier. The first objective is to develop an ocean engineering library for Open Modelica, and the second objective is to develop a co-simulation methodology to carry out the dynamic simulation of multiphysical riser tension systems using industry preferred commercial analysis software. This objective has inputs from National Oil Well Varco, who are also stakeholders in the SFI offshore mechatronics project, of which this research is a part. So NOV suggested that we develop this co-simulation methodology using Simulation X and Orcaflex, because these are the software that NOV uses for their in-house needs. In developing the Modelica Ocean Engineering Library, we analyzed different scenarios in ocean engineering operations and arrived at a framework for building the system model. And it was decided that the component models for the environment would generate parameters and feed those to the databus, from which the individual component models for non-diffracting objects or for diffracting objects or for the mooring, they would access these parameters and calculate the wave forces at their respective locations. We now discuss the development of component models, and first up is the component model for regular waves. In the development of this component model, we used the analytical expressions for the velocity potential and the wave properties based on the small amplitude wave theory and the solution to the boundary value problem. We present results to show that the outputs of the component model correspond to theoretical calculations. In formulating the component model for irregular waves, we use the principle of the Fourier series representation of the irregular sea surface and the concept of the wave energy spectrum. Our component model for irregular waves currently supports the Pearson-Moskowitz spectrum, which is a single parameter spectrum. We also present results to showcase the outputs of the component model. In developing the component model for depth varying current, we specify the depths and the current velocities at those depth points and use linear interpolation to calculate the current velocities at intermediate depths. We also use ramping to ramp up the current values and thus prevent shock loading to the other component models. This ramping was also performed in the wave component models. In developing the component model for non-diffracting floating objects, we make use of the small body assumption and specify heave loads using the Fruit-Krylov formulation and the surge loads using the Morrison equation. We present results for a free floating cylinder in waves and in current and show that the simulation results are in good agreement with Orca-Flex simulations. In developing component models for catenary mooring, we use the quasi-static catenary theory and we formulate a lookup table between the horizontal tension and the excursion of the top end of the catenary from the anchor position X. We also make use of the Morrison equation to determine the fluid loads on the mooring line itself. We present results to show that the horizontal tensions calculated by using the quasi-static catenary theory is in agreement with Orca-Flex results. We also bring out the inadequacy of using the quasi-static theory in that the dynamics of the mooring line itself are not captured during a simulation, and it also fails to capture the deflection of the mooring line due to the fluid loads. Thus, we see that we have developed component models for waves, for currents, for non-diffracting floating objects, and for the quasi-static catenary mooring. We now use the framework we discussed earlier, where the environmental component models output the parameters to a databus, from where the individual component models make use of the parameters to calculate the wave forces. And we present results that compare Modelica simulation and Orca-Flex results for a setup as shown in the diagram. And we demonstrate that there is satisfactory agreement in both cases. The work done in this direction was presented as 2 papers at the American Modelica conference. Earlier, as an introductory paper to the ocean engineering community, we presented a paper at the OMA conference in 2019, where we modeled a simple wave energy conversion system using the Modelica component based modeling approach and presented results comparing Modelica and Orca-Flex simulations to demonstrate satisfactory agreement. We also modeled a slightly different system, again using the same component based modeling methodology, and compared the energy production potentials of the 2 systems. Again, the aim of the paper was to showcase the component based modeling philosophy using Modelica, and so effects like the hydrodynamic interaction between the pontoon and the cylindrical buoy was not taken into consideration. We talked about the limitations of the quasi-static catenary theory in that it cannot capture effects of the dynamics of the mooring line itself, and that it does not account for the deflection of the mooring line caused due to the fluid loads. Hence, we decided to implement the lumped mass approach in calculating mooring forces. In the lumped mass approach, the continuous loads acting on the mooring line are discretized and applied at nodal points. From the equilibrium equation for the nodes, the equation of motion for the nodes are formulated and solved subject to the constraint equation that the links are inextensible. We adapted this method from the method presented by Walton and Polacek in their paper early in the 1960s. They had presented the method for a generic subsea cable structure without interaction from the seabed. To simulate the seabed interaction effects, we adapted the method suggested by Khan and Ansari in their work, where the reaction from the seabed is modeled as vertical forces applied on the interacting nodes. Again, in this method, the initial positions of the nodes are determined based on the quasi-static catenary theory, and the boundary value problem is then stepped up in time. We present results to showcase agreement with Orcaflex simulations. In the first case, the top end of the mooring line is held fixed at x equal to 55 meters and varying currents are applied. Again, we see that in all the three cases, there is good agreement between Mottlica and Orcaflex results. Looking at the top-link tensions, for all the three cases, again there is general agreement between Orcaflex and Mottlica results, but we notice high frequency oscillations in the top-link tensions in case of the Mottlica model. This is probably because we did not model damping into the equations of motion of the catenary. When we look at results where the top end of the catenary is moved from x equal to 55 meters to 80 meters, we see that again there is satisfactory agreement between the Mottlica and Orcaflex models as far as the configuration is concerned. But when we look at the top tensions, again we notice a general agreement, but there is the presence of these high frequency oscillations. We now look at results for the mooring catenary subjected to oscillatory flow in both Orcaflex and Mottlica. Again, we notice general agreement except for the nodal positions of node J3, where in the Orcaflex simulation the node remains grounded at all times, but in our case there is considerable motion of the node. This points to the fact that our model for the seabed interaction is inadequate. The results of the entire simulation were presented at the OMA conference in 2020. However, after performing the work, I realized my foolishness in trying to tell the Mottlica compiler how to solve the equations of motion. This is against the basic philosophy of Mottlica, because in Mottlica you build up the equations to be solved when you join the components together using connectors, and it is the Mottlica compiler that then decides how the equations should be solved. So to remedy this shortcoming, learning from our earlier mistakes, in the next part of the project when we try to model the dynamics of a chain suspended subsea load, we make use of the lumped mass approach, but instead of specifying the equations of motions directly, we build up the model using modified components from the Mottlica mechanics library, where we add real outputs to massless links such that the up segment real output transmits the location of the A flange at all times, and the low segment real output transmits the location of the B flange. This allows for the calculation of the inclination of the segment at all simulation instants, which in turn allows for the calculation of the fluid loads on the structure. Again, the incoming fluid velocity is split to the tangential and the normal component, and then the Morrison equation is used to specify the fluid loads. These are then coded onto drag and buoyancy blocks, and the forces are applied to point masses that model the mass of the segment. The segments are interconnected using revolute joints, and thus the chain is built up. We look at the results and we see that there is excellent agreement between Mottlica and Orcaflex results in this case, and that the Mottlica model also simulates quite efficiently. Again, looking at the configuration of a chain suspended load when subjected to uniform current, we see that there is excellent agreement between Mottlica and Orcaflex results. Even for the non-uniform current profile case, there is good agreement. Looking at the top link tensions, we see that there is a reduction in the top link tension as the fluid loads now support a part of the weight of the chain and the suspended load. But in the non-uniform case, we see that Modlica shows a slight reduction in the toppling tension, while Orcaflex shows a slight increase in the toppling tension. But this difference is not significant. We present results for the horizontal and vertical response of the suspended subsea load. Again, we see that there is good agreement between Modlica and Orcaflex, and also excellent agreement as far as the top end tensions are concerned. We also present results when the configuration is subjected to a current plus a regular wave. Again, we notice that there is good agreement between the Modlica and Orcaflex results. This work is presented in a paper in the Asian Modlica conference. Coming to the hydrodynamics of diffracting objects, we discussed that we need to carry out frequency domain hydrodynamic analysis to determine the frequency dependent parameters. Most of the hydrodynamic analysis software are commercial and black box in nature, so it was decided that we would develop our own hydrodynamic analysis package using Python, which is open source. In formulating the problem, we express the velocity potential in the vicinity of a floating object as the sum of velocity potentials due to the incident wave, the diffracted wave, and the radiated wave. The incident wave velocity potential is known, and the diffracted and radiated wave potentials can be determined from the linearized body boundary condition. The Bernoulli equation relates the pressure to the velocity potential, and once the potentials are known, you can calculate the hydrodynamic pressure loads and the hydrostatic pressure loads. Again, from the definition for the diffraction and radiation potentials, you can calculate the wave excitation loads, which comprise of the Fruit-Krylov loads, and the diffraction loads, and the wave radiation loads, which comprise of the added mass and damping. In the determination of the velocity potentials, we make use of the Green function method suggested by Lamb, where he represented the field velocity potential as an effect of source distributions on the body in the case of an infinite fluid domain. From the expression for the velocity potential, we see that the value inside the parenthesis represents the source strength, while minus 1 by 4 pi r is the free space Green function. In the case of a free surface and waves, the Green function changes. It now has a stationary part and an oscillatory part to account for the effect of waves. Teleste and Noblesse give numerical expressions for the evaluation of the wavy part of the Green function and its derivatives. They also provide the printout of a Fortran code along with their publication. We replicate the Fortran code and wrap it for use in Python using the F2Py interface. Now the body boundary condition can be expressed as a boundary integral equation, and in the evaluation of this integral equation we make use of the Cauchy principal value integral, because the Green function is singular at the body surface. We then use the Hess-Smith panel method to convert the boundary integral equation into a set of equations containing integrals evaluated over flat quadrilateral panels. Hess-Smith had approximated the body surface by using flat quadrilateral panels, each having a constant source density distribution. This allows the expression of the Green function and its derivatives in terms of integrals of the form 1 by r and its derivative evaluated over flat quadrilateral panels. Another important contribution of Hess-Smith was the analytical expressions for evaluating integrals of the form 1 by r and its derivatives over flat quadrilateral panels. From the analytical expressions for the directional derivatives, we note that the x and y directional derivatives go to infinity at the panel edges, and the normal directional derivative is singular at the centroid point. In our code, we avoid this singularity by assuming that the source panels lie at a small distance beneath the body panels. In the evaluation of the integrals of the wavy part of the green function and its derivatives over flat quadrilateral panels, we make use of the consideration that the wavelength is quite large compared to the panel dimension. And so the wavy part of the green function associated with the panel is constant over the panel. And this allows for the evaluation of the integral as a simple multiple of the wavy part of the green function with the associated panel area. Again, we note that the wavy part of the green function and its derivatives are given by the Fortran code, which is wrapped in F2π for our use in Python. We now have ways to evaluate all the terms of the green function. And so the set of equations that involved integrals over panels is now transformed into a set of linear algebraic equations. And we may now formulate the alpha matrix, where each element of the matrix gives the normal velocity induced at the center of panel I due to all other panels j. And using matrix operations, we can now calculate the source densities associated with each panel. Once the source densities are known, we can calculate the velocity potentials for each mode of the body for different frequencies. Once we have the velocity potentials, we can calculate the wave radiation forces as well as the wave excitation forces. The whole procedure is implemented as a Python code, and the algorithm is well explained both in the thesis as well as in the paper that is submitted to a journal. We then present a whole range of results to demonstrate the various aspects of the code. We present results, for example, to demonstrate what happens if a body is introduced into an infinite flow domain. We present results to explain the effect of the free surface and of the image source. We present results to explain the physical significance of radiation waves. We then present results from the hydrodynamic analysis of a submerged cube. We also present panel convergence results. We then present the results for the hydrodynamic analysis of a barge structure, both using our code and using ANSYS Aqua, and we demonstrate that there is satisfactory agreement between the radiation loads and the wave excitation loads. We also bring out the shortcomings of our code in that the irregular frequencies are not removed. The entire work done in this direction has been submitted to the MIG journal. Coming to the development of the co-simulation methodology for top tension risers. From the figure, we notice that riser tensioning prevents compression buckling when the platform moves down, prevents excessive tension loads on the riser when the platform moves up under the influence of environmental loads. It also limits riser deformation due to current loads, which would otherwise hinder drilling activities. It also ensures a clean liftoff of the LMRP from the BOP in the event of a riser disconnect. Usually two types of riser tensioners are used. In the wireline tensioner, it is a wire rope that transmits the tensioner cylinder force to the riser, while in the direct acting type tensioner, the tensioner cylinder is directly attached to the outer sleeve of the slip joint. In both cases, the hydrodynamic circuit remains the same. In the conventional approach, the riser tension system is simplified and represented using linear or non-linear spring damper elements, and the riser analysis is carried out using global riser analysis software like Arcaflex. In the mechanical model approach, the entire system is modeled as a spring mass damper system, where the stiffness of the riser tensioner system is then specified based on the pressure volume relations, while the damping of the riser tensioner system is obtained from the damping curves of the anti-recoil valve. Both these methods involve the simplification of the riser tensioner system. To overcome the deficiencies associated with the simplification of the riser tensioner system, Ronnie Sten, who also happens to be my co-supervisor, used the multiphysics software Simulation X to formulate the parametric model of the DAT cylinder. He then used this parametric model to specify the spring damper model of the tensioner in Reflex, which is a global riser analysis software. He also proposed the establishment of an integrated model with direct communication between the riser analysis software and the multiphysics software. Our methodology is an extension of that suggestion. Here we use Python to enable the direct communication between OrcaFlex and Simulation X. We model the riser tensioner system in Simulation X. We model the platform and the riser in OrcaFlex, and we use an API interface to facilitate the communication between both the software. We present representative simulations to demonstrate the methodology. Here we try to simulate the dynamics of a pneumatic cylinder carrying a load at the free end of its piston. The system can be modeled entirely in Simulation X using component models already available in the Simulation X library. In developing the co-simulation model, we model the mass in OrcaFlex and we attach it to the end of a winch wire, which is concealed by this mock-up of the cylinder arrangement. The actual pneumatic cylinder is modeled in Simulation X, and the API interface provides for the communication between both software. At each simulation time step, the load acting at the end of this winch wire is transmitted as the load acting at the end of the piston rod, and the dynamics of the cylinder are then simulated, and the velocity of the piston rod is passed on to OrcaFlex as the payout rate of the winch wire. We provide end-stop arrangements since the winch wire cannot handle compression, and so the hit of end-stroke forces would not be transferred to the mass unless this end-stop arrangement was not given. In simulating the connected condition of the pneumatic cylinder arrangement, we specify a sinusoidal motion to the suspended load. This can be done in Simulation X using a position constraint and feeding a sinusoidal signal to that. This can be done in the co-simulation model by attaching the load to a vessel object and specifying a time history motion to the vessel object. On comparing the results, we see that there is excellent agreement between the pure multiphysical simulation results and the co-simulation results. This simulation was for a frictionless cylinder. We can include friction in the cylinder by specifying the friction using Strybeck curves in both the pure multiphysical case as well as for the co-simulation case. Again, looking at the results, we see that there is excellent agreement between the results. In simulating the recoil condition of the cylinder, we hold the piston rod extended initially and then release the load. This can be modeled in the Simulation X model by specifying an initial position for the load, and this can be simulated in the co-simulation model by using a detachable link and releasing the load at the required time. Again, on comparison of the Simulation X and co-simulation results, we see that there is excellent agreement. We also demonstrate the effectiveness of the end-stop arrangement had the end-stop not been present, as shown by the blue line. The small segment of riser that is modeled in the OrcaFlex model would not go into compression when the cylinder hits end stroke. But with the end stops model, we see that as the cylinder hits end stroke, the riser element goes into compression. And so we see that overall there is satisfactory agreement between the pure multiphysical simulations and the co-simulation model developed. To demonstrate the effectiveness of the co-simulation methodology in realistic conditions, we model a simple system where the riser passes through a moon pool of a buoy to attach to the riser tensioner cylinder. Again, the riser tensioner is modeled in Simulation X, while the buoy and the mooring and the riser is modeled in OrcaFlex with API interface between OrcaFlex and Simulation X. We now look at the calm water disconnect of the arrangement, where the buoy is floating in calm water and the LMRP is disconnected at 0 seconds into the simulation. As soon as the LMRP is disconnected, the cylinder begins to retract, the LMRP rises, the cylinder hits end stroke, and this is also reflected in the motion of the LMRP. Also, as the cylinder hits end stroke, momentum is transferred from the riser stack onto the buoy and the buoy starts bobbing up and down. We also notice other effects like the top end of the riser going into compression as the cylinder hits end stroke. We also notice multiphysical effects like the pressure temperature relations, where as the cylinder retracts, the HPV pressure drops and there is a corresponding drop in the HPV temperature. After the cylinder comes to rest at the top end position, there is heat transfer from the surroundings into the high pressure vessel and the temperature begins to rise. A similar behavior is also noted in case of the low pressure vessel. Let us now have a look at the simulation itself, where the riser is disconnected, it hits end stroke, and the buoy starts bobbing up and down. Let us look at a case of the wave disconnect. In this case, we have deliberately chosen the waves to be high enough that when the buoy rides the wave crest, the cylinder hits the piston hits the gland end of the cylinder. And so we expect a spike in the effective tension of the riser stack as shown by the effective tension plot. There are spikes when the buoy rides the crest of the wave. The riser is disconnected at 20 seconds into the simulation. As the LMRP is disconnected, the cylinder begins to retract and it hits end stroke a few times and then comes to rest. We see that again the effective tension of the riser goes into the compression region as the cylinder hits end stroke, and all the other multiphysical effects are also captured. Let's now have a look at the simulation itself. Initially, the riser is connected and the buoy is responding to the wave. At 20 seconds, the riser is disconnected but now, and it retracts, its end stroke and comes to rest, and the platform continues to respond to the waves. Coming to the full scale model, again the platform and the riser stack is modeled in Orcaflex. We model all the 6 tension cylinders and we provide a unified end stop arrangement for all the 6 cylinders. Again, the tensioner system itself is modeled in Simulation X with the API interface providing the communication between both software. To validate the performance of the full scale model, we use field data provided by NOV, where we analyze the data and isolate a planned riser disconnect event. Since the platform and the riser stack were modeled on NOV provided data corresponding to the field conditions, we now simulate the disconnect procedure using the co-simulation methodology and compare the responses with the field measurements, where the red line shows the field measurement and the blue line shows the simulation results. We notice that there is satisfactory agreement between the co-simulation model and the field measurements. The real advantage of the co-simulation methodology comes into the fore when we talk about advanced simulations. For example, if we want to optimize the initial pressure of the HPV by deciding whether to use 52.5 bar pressure or 60 bar pressure, in such a case we need to carry out a series of simulations and simulate the riser disconnect at various phases of the platform motion for both the pressures, and then see if in any case there is an interference between the LMRP and the BOP after disconnect. We notice that when we use 52.5 bar pressures, in 2 instances the LMRP interferes with the BOP, and so 60 bar pressure is the optimal pressure to use. We can include further effects like the effects of line friction by modeling the pneumatic and hydraulic lines in the simulation model for the riser tensioner system. Again, on carrying out an irregular wave analysis, we notice that the effect of line friction on the system response is not very significant in this case. By adding more components into the multiphysical model for the riser tensioner system, we can simulate the whole disconnect procedure. For example, by adding a vent valve, we can simulate the disconnect procedure from connected condition to pull off, to disconnect, to hard hang off, and then finally ending in a soft hang off the riser. Here we see that the platform begins to pull away from the wellhead at 20 seconds, and immediately after the platform begins to pull away, the riser is disconnected. The LMRP begins to rise as the riser is disconnected and the tensioner cylinder begins to retract. As the tensioner cylinder reaches a low stroke value, it is locked in position to prevent the riser from dropping down and the LMRP from interfering with the BOP. the platform continues to move to a safe location, and once it has reached the safe location, the vent valve is opened, the HPV pressure reduces, and the riser stack and the LMRP is lowered, and the platform continues to respond to the waves with the riser in the soft hang-off condition. Let's now have a look at the simulation. Initially, the platform is responding to the wave and the riser is in the connected condition. At around 20 seconds, the platform will begin to pull away. As the platform pulls away, the riser is disconnected, the cylinder stroke reduces. The platform pulls away to a safe position, and the vent valve is opened, and the LMRP and the riser stack is now lowered, and the platform continues to respond to the waves with the riser in the soft hang-off condition. This brings us to the end of the presentation. We now look at the contributions of the work. We saw that we developed component models for regular waves, irregular waves, depth varying current, non-diffracting floating objects, and quasi-static catenary moorings. We packaged all these component models to constitute the Madlika Ocean Engineering Library. We also present research outputs towards the development of component models for subsea cable structures based on the lumped mass approach, and for component models for simulating the hydrodynamics of diffracting floating objects. We also present a co-simulation methodology for tensioned risers and demonstrate its effectiveness. Further research can be in the direction of refining the component models for the frequency domain analysis, in developing component models to carry out time domain simulation of the vessel based on hydrodynamic parameters obtained from the frequency domain analysis, component models for winches, pulleys, thrusters, the dynamic positioning system, and for a generic knuckle boom crane. We can also develop component models to simulate the effect of wind loads on the platform, and a lot more. The end effect of developing all these component models would be that we would then be able to simulate systems as illustrated by the figure, where there is severe weather condition at the sea surface, but the deep water conditions are calm, and then we use a drone to carry out subsea installation. In this case, the crane wire can be left slack, which allows for the vessel to drift from its optimal position under extreme weather loads, but the subsea construction activities would continue unaffected. Further research in the direction of the co-simulation methodology can be to develop a control system to prevent the riser from hitting the end stroke as it recoils. This can be, for example, done by having a high pressure vessel with a valve arrangement which boosts the LPV pressure in case the control system detects that there is a possibility of the riser hitting end stroke. We can also optimize the closure curve of the ARV using the co-simulation methodology. The possibilities are endless. Let's imagine a scenario where humans have to leave Earth in the not so distant future. Let's say that we have identified a planet with air and water and lots of it. In fact, the whole surface of the planet is a big ocean. Let's say that the first generation of humans have already started the journey. It will be their grandchildren or great grandchildren that eventually colonize the planet. They have limited resources, so they must optimize their actions once they go into orbit around the planet. And they would like to build a platform for the spaceship to dock once it enters the atmosphere. To make efficient use of the resources, they would then need to model different scenarios under which the installation process would proceed. And in such cases, the only way is to use multiphysical modeling. Multiphysical models are the only way to understand how a yet to be built system would behave, and they seem to be the only way to evaluate pioneer engineering endeavors. With that, I come to the close of my presentation, and I hope that I've been able to give you a good idea of the research that I have done during the course of my PhD. Thank you.